Multivariable calculus, we're in lesson 15.9, and we're going to deal with our last type of coordinates today. There is yet another one, spherical coordinates. You can see at our top of the page, I can convert points, ordered triples, between spherical and rectangular coordinates. We can also evaluate integrals in spherical coordinates. So let's read right up here. The last time in 15.8, we worked with cylindrical coordinates. Today, we learn about the spherical coordinate system, which is very helpful evaluating triple integrals bounded by spheres and cones. Now, spherical coordinates are in an ordered triple form, but it's not an x, y, z. There will be a rho, that's your radius, we see that right there. We have a theta. Theta is much the same way that we've been working in polar coordinates as well. Theta is the angle made with the positive x-axis. But then we have phi, and phi is an angle made with the positive z-axis. And phi is only going to be between 0 and pi radians. So phi, if we come right here, you can see I'm going to highlight it. Phi is, like we said, the angle made with the positive z-axis. So, as we take a look at this point right here, you would move so many radians to get there. If we're below the xy plane, if our point was underneath the xy plane, then we will go greater than pi over 2 radians, but will always be less than or equal to pi radians. So that's very, very important for us to realize. It's just these three coordinates, rho, theta, and phi. So here are some common graphs that you could definitely benefit from. Look how simple it is to write the equation of a sphere. If you just said rho is equal to a constant, like rho is equal to 4, you would move 4 spaces in the x, y, z direction, left, right, up, down, you name it, you would create a sphere. What if theta was equal to a constant? Let's just say theta was equal to pi over 4. If theta was equal to pi over 4, you would get a half plane. Look at phi. If phi was equal to something, like let's just say it was equal to pi over 4, you could say find all those points that would be pi over 4 radians away from the z-axis. And no matter how you do that, you'd create this cone. If you are larger than pi over 2 but less than pi, then your cone goes below the xy axis, xy plane. So let's get to the relationship between rectangular and spherical coordinates. I think so very importantly we can take a look at this point right here, an x, y, z, and you can think, okay, so we're also going to represent that with a rho, theta, and a phi. Well, take a look at this point at the origin and this point in question right here. That's the distance formula, isn't it? And the distance formula in 3 dimensions looks so very much like what we have in 2 dimensions. We just throw in a z coordinate being subtracted as well. But of course, if our x1, y1, z1 was 0, 0, 0, the origin, and if we had this other one, well, then we could, just have a point x, y, z, and if we said that's our second point, well, you could quickly see that that distance then would be, x minus 0 squared plus y minus 0 squared plus z minus 0 squared. And we could square both sides to get d squared is equal to x squared plus y squared plus z squared. But what is d? D is that distance which we are designating as rho. So I've got this box right here. This is one amazing link between the two systems. x squared plus y squared plus z squared is equal to rho squared, where rho is that radius from the origin to the point in question. It's that distance. Now, you can see, actually, I've highlighted the triangle in green down below. You know, we always could fall back to an x and a y coordinate, and, you know, you could definitely say, well, you know, then we've got this r right down here, and r, of course, was really in our polar scenario, you know, especially as we were learning about that in Calc BC, and we could say from the Pythagorean theorem, x squared plus y squared equals r squared. We know that x is equal to r cosine theta, y is equal to r sine theta, and then tangent of theta would be y all over x. But wow, how do we make a jump and start talking about linking up all of this information about phi? Well, what I'd like to do right now, I'd like to really just show you that, you know, this point in question, the x, y, z, which we've got right up here, you know, we can rotate from the positive z-axis and say that's phi. And, you know, very quickly, if you're on your toes, you're going to realize that we could build a rectangle right here. We could drop down this point, P, down to x, y, 0, call that P prime, and you will have parallel sides here. You can more or less see very quickly that if this would be a height of z, this would be a height of z also. You've really built yourself a rectangle. And you can say, here's your r down here. Well, that means we've got r up above. And what are we really dealing with? Well, my goodness, very nicely, all of a sudden you're going to be able to see in a nice systematic way that we could take either one of these yellow triangles and do some trig with them. Let's just go ahead and perhaps link in SOHCAHTOA. This would be opposite of phi. This would be your adjacent side right here. And of course, here's your hypotenuse. So I'm looking at, you know, triangle QOP, this right triangle. So I could say the cosine of phi is going to be adjacent all over the hypotenuse. And my goodness, all of a sudden I can solve for z. And I'll know that z is equal to rho times the cosine of phi. And that's super, super, super helpful. All of a sudden we have a link between these two systems. Just like we had a link between x squared plus y squared plus z squared equals phi squared. But look, I want to take it a step further. We could take the sine of phi. Now the sine of phi is going to be opposite all over the hypotenuse. And what does that really mean? Well, you can quickly solve for r and get that r is equal to rho times the sine of phi. However, look at what x is. And I'm going to bring this over here. X is equal to r cosine of theta. But what's r? R is really rho times the sine of phi times the cosine of theta. You know, that's like your r cosine theta, so to speak. Wow. Likewise, look at y. Y right here is r sine of theta. But what's r? Well, r is what we have right here. It's rho sine of phi sine of theta. So guys, very, very, very importantly, I'm going to highlight these in blue. When we're going between the two coordinate systems, we most definitely want to hold on to what I have highlighted in blue. And I'm going to put some stars around here. Super, super, super importantly, These are our links to going between these two systems. And, we're going to actually start off with just doing that very same thing. We're just going to go between one coordinate system and another. Let's do that right now. We're going from spherical to rectangular. So we know what rho is. We know what theta is. And we know what phi is. And they're saying, hey, could you go from the spherical to get an x, comma, y, comma, z? Well, you can flip back to our notes on the front page there. But my goodness, I hope you can see in that blue box, and actually we had several blue boxes, didn't we? What's wonderful here, just referring back, you're going to be able to have this link to know what x, y, and z are here. And of course, you also have x squared plus y squared plus z squared equals rho squared. But look at this, very fast. We can say, well, rho is a 2, and then we'd have the sine of pi over 3 times the cosine of pi over 4. Well, what is the sine of pi over 3? Well, it's root 3 over 2. And here we get root 2 over 2. Well, these 2's are going to cancel. And that means our x is going to be radical 6 all over a 2. We come right over here, and it's pretty much the same thing, isn't it? 2 times the sine of pi over 3. The only difference now is we'll have the sine of pi over 4 for our theta. We still get a root 2 over 2. This time, the sine of pi over 3, well, we still have this root 3 over 2. You're going to look at this and say, my gosh, it's like the same problem. The same answer, and it is, because sine of pi over 4 and cosine of pi over 4 are the same values. Z is going to be different, isn't it? We'll have 2 times the cosine of pi over 3, because that's what phi is. Cosine of pi over 3 is a half. This is going to be a 1. So it won't take you too long to see that in our rectangular system, we'll have radical 6 over 2, radical 6 over 2, and then a 1. Right now, we're going to go in a very different direction. We are going from the XYZ, rectangular, and we need to go to spherical. Well, here we go again with this very important link between the two systems. X squared plus y squared plus z squared equals rho squared. So we'll have 0 squared. Here we'll have 2 root 3 squared. Here we have negative 2 squared. And this is 4 times 3, which is a 12. This is a 4. And rho squared equals 16. We're going to have the square root and just have rho is equal to 4. Once you know what rho is, my goodness, that can really help you tremendously. If we found phi, that could really help us out. Our z, we happen to know, is negative 2. Now we know that rho is 4. And when we divide both sides by 4, we'll have cosine of phi is negative 2 over 4, which is negative 1/2. Now remember that inverse cosine only gave answers between 0 and pi. And when we're negative, we have to be in the second quadrant. We'll have a reference angle of pi over 3, but in the second quadrant, that's 2 pi all over 3. Here's another wonderful link. You might remember I also put a little box around this, that the tangent of theta was equal to y over x. That's something that we remember from long ago. And wow, would you look at this? This is undefined. 2 root 3 over 0, and you think, gosh, where is tangent going to be undefined? Well, theta is going to be going between 0 and 2 pi. So we could definitely jump in and say this is going to be at pi over 2. So as we write out our ordered